Welcome to the last video on cooperative games. This is the 7th video and the third and last one on the Shapley value. In the previous video we looked at how to compute the Shapley value for 2-player games, and in this video I will look at 3-player games, in particular the three examples that we examined before: the factory workers and the capitalist, the landowner, and the software developers. Okay, so let's start with a simple example not related to those three. So suppose that we have 3 individuals. All these examples will be 3 players, games with 3 players, so n is the set 1, 2, 3. So in this case we have that each individual alone cannot produce any surplus. Individual 1 with 2 or with 3 can produce a surplus of 4, and individuals 2 and 3 can produce a surplus of 8. So let's see what the Shapley value assigns to each player. Remember the metaphor is we have a room that is empty, and then the players arrive one after the other, and we give to each player the change in the surplus from the situation before his arrival and the situation after his arrival. So he gets a marginal contribution, and we look at all possible ways in which the players could arrive, all possible orders of arrival, and then we consider them all equally likely. So we then compute the average marginal contribution of each player. So the players can arrive in the following order: first 1, then 2, then 3, or first 1, then 3, then 2, or first 2, then 1, then 3, or first 2, then 3, then 1, or first 1 and then first 3 and then 1 and then 2, or first 3 and then 2 and then 1. Okay. Now let's compute the marginal contribution of player 1. Remember that, as usual, V of the empty set is 0. So before he comes we have 0, after he comes we have 0. So if player 1 comes first, his marginal contribution is 0. We can, let's use different colors for different players. If we look at the marginal contribution of player 2, now symmetrically, if player 2 comes first, then her marginal contribution will be 0, right? Because the value is 0 before she arrives and 0 after she arrives. And if we're looking at the marginal contribution of player 3, when player 3 arrives first, then her marginal contribution will be 0. Now let's go back to player 1. If player 1 comes after player 2, then we go, so when player 2 is in there, the value is 0, and then player 1 comes and the value becomes 4. So the marginal contribution of player 1 is 4. If let's skip 1 and go to 3, 1, 2. When player 3 is there first, the value is 0. Then player 1 comes and the value jumps to 4. So player 1's marginal contribution is 4. And now let's look at the case order of arrival 2, 3, 1. When 2 and 3 are there is 8. And what is the marginal contribution of player 1? Well, I forgot to give one crucial piece of information, which is what V of n is. And I now remedied it. I added V of n is equal to 10. So now we can compute the marginal contribution of player 1. If the order of arrival is 2, 3, 1, when 2 and 3 are there, the value is 8. 1 arrives and it goes up to 10, so it's 2. And of course it doesn't matter in the order in which 2 and 3 arrived. Again, this is 2. Okay. Then we go to player 2. Marginal contribution of player 2. When player 2 arrives after player 1, then we go from 0 to 4, so the marginal contribution player 2 is 4, and if player 2 arrives last after 1 and 3, then we go from 4 to 10, so the marginal contribution of player 2 is 6. If player 2 arrives after 1 and the same is here, of course, here. When 1 and 3 are in the room, we have 4, and then when all of them is 10, so 10 minus 4 is 6. And then finally, if player 2 arrives after player 3, then we go from 0 to 8, so a marginal contribution is 8. And then we go to player 3. When player 3 arrives last after 1 and 2, then there is a jump from 4 to 6. After and the same is true down here, where 2 and 1 were there before 3 arrived. Then in the second one, 1, 3, 2, player 3 arrives after player 1, so we go from 0 to 4, so her marginal contribution is 4. And then 2, 3, 1, player 3 arrives after player 2, we go from 0 to 8, and the marginal contribution is 8. So now we take each order of arrival to be equally likely. So let's write the probability here. Probability is 1/6 for each. There are 6 possible orders of arrival. And so the Shapley value is as follows. For player 1, we have 1/6 times 0 plus 1/6 times 0 plus 1/6 times 4 and so on. Collecting the 1/6, we have 1/6 times 0 plus 0, and then 4 plus 2 plus 4 plus 2. So this is 8, 10, 12. 12 divided by 6, which is equal to 2. For player 2, let's keep the same color. For player 2, it is 1/6 of, and then ignoring the zeros, is 4 plus 6 plus 6 plus 8, which is so 66, 12, 20, 24 divided by 6, which is equal to 4. And then we have for player 3, where 1/6 of 6 plus 4 plus 6 plus 8. 6 plus 4 plus 6 plus 8, and that's again 24. So 20 divided by 6 is equal to 4. So the Shapley value gives player 1 less than players 2 and 3, gives 2 to player 1, 4 to player 2, and 4 to player 3. Note that this imputation 2, 4, 4 is in the core, because the core is the set of imputations x1, x2, x3, such that where each is xi is greater than or equal to 0, okay, so let's write it xi greater than or equal to 0 for all I. Then x1 plus x2 greater than or equal to 4, x1 plus x3 greater than or equal to 4, x2 plus x3 greater than or equal to 8, and x1 plus x2 plus x3 equal to 10. So this is in the core, but it's not the only imputation in the core. There are more. So other imputations in the core are, for example, 0, 5, 5. Player 1 gets nothing. Or 1, 5, 4, or 1, 4, 5, etc. So there are many imputations in the core. Only one is the Shapley value. So this is one example where the Shapley value is in the core, but we saw that in general this is not the case. So now let's look at the examples that we had in the past. We looked at the core for those examples, and now let's look at the Shapley value. So the first example, there is a capitalist who owns a factory and 2 workers, and production requires the factory and at least 1 worker. So the cooperative gain can be written as V of I equal to 0 for every I. V of 2 and 3, the 2 workers together get 0, can produce 0, but 1 and 2 and 1 with 2 and 1 with 3 can produce 3,000, and 1 with 2 and 3 can produce profit of 6,000. So you might want to pause and see and do the calculations yourself, and then check later on if your calculations are correct. So I'm not going to use different colors anymore. Let's have the computation for the marginal contribution of the 3 players. When player 1 is first, his marginal contribution is 0. When player 2 is first, her marginal contribution is 0. When player 3 is first, her marginal contribution is 0. Then when player 1 is second after player 2, we go from 0 to 3,000. So I'll put a 3, well, let's put 3,000. We go from 0 to 3,000. If 2 and 3 are already there, and then 1 comes after, then we go from 3,000 to 6,000, so it's another 3,000. If player 3 is there and 1 comes after that, then we go from 0 to 3,000. And if players 3 and 2 are there and 1 comes last, then again we get 3,000. Marginal contribution of player 2, if arrives second after player 1, we go from 0 to 3,000. If player 2 arrives last after 1 and 2, then we go from 3,000 to 6,000, so again 3,000. If player 2 arrives same thing here, 3,000. We go from 3,000 to 6,000. And if he arrives second after player 3, it's 0 with player 3 is there, then 2 arrives, 2, 3 is still 0, so the marginal contribution is 0. And for player 3 arrives last, then we go from 3,000 to 6,000. If arrives second after player 1, then we go from 0 to 3,000. If he arrives last, then we go from 3,000 to 6,000, so 3,000. Second after player 2, then we go from 0 to 0. So these are the marginal contributions. And now, again, each order we take to be equally likely. So the Shapley value is, for player 1, is 1/6 of 3,000 plus 3,000 plus 3,000 plus 3,000. So that's of 12,000 is equal to 2,000. Okay, so I didn't do things correctly. When we look at player 1, if player 1 comes after player 2, then we go from 0 to 3,000. But if player 1 comes after 2 and 3 are there, we go from 0 to 6,000. So that should have been a 6,000. And the same at the bottom, where player 1 comes after 3 and 2. When 2 and 3 are there, they get 0. Then player 1 comes and we jump to 6,000. So what is in the bracket here is 6, 12, 15, 18,000. So 1/6 of 18,000, which is 3,000. Okay, so then for player 2, we got 1/6 off, and then we have 3,000 3 times, so 1/6 of 9,000. Which is 1,500. And player 3, well, player 3 and 2 are interchangeable, so they should be getting the same amount. And in fact, it is 1/6 of 9,000 for also player 3, so we get 1,500. Okay. So yes, so notice here that players 2 and 3 are interchangeable, so it's enough to compute the Shapley value for one of them, then the Shapley value for the other will be the same. This is one of the axioms of Shapley. Now, what was the core for this game? The core was very large. It contained all sorts of things. For example, full exploitation of the workers. Player 1 gets 6,000 and the workers get 0. Or full exploitation of the capitalists. The workers together get $6,000 and the capitalist gets nothing, and a whole lot of other different imputations. But in this case, we do have that this imputation is in the core. So the imputation 3,000, 1,500, 1,500 is in the core, but the core contains many more imputations. Now let's look at the example of the software engineers. The example is described in words there and translated into the characteristic function that assigns 200 to the singleton 1, 300 to the singleton 2, 0 to the singleton 3, and then 1 and 2 together get 800, 1 and 3 together 500, 2 and 3 together 650, and the 3 of them together get 1,000. So again, this is a good place for you to pause, do the calculations, and then compare them at the end. Okay, so this is what you should have got. We have the usual 6 orders of arrival on the left, and then for each order of arrival we compute the marginal contribution of each player, and these are the values. And now so the sum of the marginal contributions of player 1 is 2,100, so the Shapley value assigns the following payoffs. So for player 1, is 1/6 of 2,100, which is 350. For player 2, it is 1/6 of 2,850, which is 475. And for player 3, it is 1/6 of 1,050, which is equal to 175. So according to the Shapley value, these 3 people should get together, sign a contract, agree to put all the software together into an office suite, and then they divide the total profit of $1,000 as follows. Player 1 gets $350, player 2 gets $475, and player 3 gets $175. And once again, let's compare this to the core. We have that the Shapley value, which is 350 to player 1, 475 to player 2, 175 to player 2, is in the core, because the core, as we saw previously, the core is the set of x1, x2, x3, such that what do we need? We need x1 should be at least 200, x2 should be at least p of 2, which is 300, x3 can be any non-negative number, but then we need x1 plus x2 to be at least 800, x1 plus x3 to be at least 500, and x2 plus x3 to be at least 650. And then finally we need the sum plus x2 plus x3 to be equal to 1000. And the Shapley value satisfies all these inequalities, so is in the core, but the core contains many more imputations. In fact, any imputation that satisfies all these inequalities. So this is another example where the Shapley value is in the core, but we know that in general it's not the case. The last example of a three-player game that I want to look at is the one that we looked at before. You have a landowner who can either use it for agricultural purposes or give it to an industrialist who will then build a factory and sell the factory and the land, or give it to a real estate agent who can build residential units and then sell land and residential units. So we translated the verbal description into these the cooperative game written here, and now let's see what the Shapley value is. So I will pause and write down and then come back. Okay, so here are the calculations, the usual 6 orders of arrival, and player 1 is the landowner, player 2 is the industrialist, and player 3 is the real estate developer. For each order of arrival, I've written the marginal contribution of each player, and now finally we get that the Shapley value is as follows. For player 1, we have 1/6 of 1,300,000, which is equal to 216,667. For player 2, it is 1/6 of 100,000, which is 16,667, and for player 3 it is 1/6 of 400,000, which is equal to 66,667. So with some approximation, so they add up to a little bit more than 300,000. Okay, so now this is an interesting game because the Shapley value is not in the core, because when we looked at the core for this game, we saw that if x1, x2, x3 is in the core, then x2 must be equal to 0. So individual 2 is the industrialist, and at any imputation in the core, the industrialist gets nothing. And we observed that that was not really a fair arrangement, because the industrialist is useful in this game. It's useful for player 1, the landowner, because he's able to extract a lot of money from a deal with a real estate agent, precisely because he has this credible threat of going to the industrialist and making a deal with him. So while the core does not recognize this positive role that the industrialist plays and gives him nothing, the Shapley value does recognize this role and gives him a payment of $16,000. So it's possible that you have a game where the core is non-empty. In fact, in this game, the core is non-empty. We characterized it when we were talking about the core, and yet the Shapley value is not in the core. So the Shapley value can be in the core. The core might be empty, and yet the Shapley value is always there. So that's one example where the Shapley value is not in the core. But it's also possible that the Shapley value is not in the core, even though the core is non-empty. And now I basically want to conclude here, but let's consider a case where there are 4 players. Now, once you understand what the algorithm is, you can apply it to any number of players. Now, the order of arrivals is the number of permutations of the number of players. So when you have 2 players, you have 2 factorial, which is 2 possible orders of arrival. If you have 3 players, then the number of order of arrivals is 3 factorials, which is 1 times 2 times 3, which is 6. Now, when you have 4 players, you have 4 factorial, which is 24 possible orders of arrival. So it's quite time-consuming to calculate the Shapley value. It takes a lot of time and computation, but it can be done. Right? So I want to give an example where it takes no time at all. Okay. So let's consider this case. V of I is equal, say, to 2 for every I. Then V of I j is equal to, say, 6 for every I j. So one individual alone can get a surplus of 2. 2 individuals together, whoever they are, 1 and 3, 1 and 4, 2 and 3, and so on, can get 6. V of I j k is, say, 10. So 3 individuals together can get 10, and whoever they are, so 1, 2, and 3, or 1, 3, and 4, and so on. And finally, V of n, say, is 44. Do we want to embark in a whole lot of computations? And the answer is no need to, because any 2 players are interchangeable. So then what does the Shapley value say? For interchangeable players, they must be getting the same amount. Must be getting the same amount in the Shapley value. So any 2 players must be getting the same amount. So that means that every player gets the same amount. So the Shapley value then is 11, 11, 11, 11. Is V of n divided by 4. So this is one case where we can just make use of the axioms very quickly and compute the Shapley, well, without even computing, and infer what the Shapley value is. Okay, so I'm concluding both the topic of Shapley value and the overall topic of cooperative games. There is much more to cooperative games than what I've talked about. There is the Nash bargaining solution, which is an interesting one. There are many different solution concepts besides the core and the Shapley value, the nucleolus, the kernel, the stable set, and so on. But here you get an idea of what cooperative game theory is about and what approach you can take in cooperative game theory. Do you want to take the rationality approach and just see what one could recommend to players under the subject to the restriction that the players are rational, they could reject some recommendations? Or do you want to first of all establish some general principles of fairness and tell the players, look, if you agree with these principles, then you must accept this recommendation because this is what follows from those principles, and that's what the Shapley value does. So there are these two different approaches in cooperative game theory, and so if you're interested, you can look up some reference in general cooperative game theory. So this concludes the topic of cooperative game theory.